Okay, so let's get started. Good morning, good afternoon, or good evening, everyone, depending on your location. I'm Koji Yamashita, the moderator of today's webinar from UC Riverside. I'm serving as the PS chair of the Algebra Footage section. The first off, welcome to the Algebra PS Footage section webinar. Our footage section spans a wide geographical area stretching from West Covina to the eastern edge of California and from Temecula to Baker. Today, we are honored to welcome a distinguished speaker from Brazil, Professor Glauco Taranto. As Brazil rapidly transitions from a hydro-dominated system to one with large amount of wind and solar generation, its vast AC network and expanding HVDC infrastructure face new operational challenges. Today, Dr. Taranto will discuss how advanced HVDC control and hybrid AC-DC coordination can enhance stability and improve interregional power flow across the Brazilian grid. Thank you for joining us, Professor Taranto. And before we begin, let me offer a brief introduction to his background. Dr. Glauco Taranto received his BS from the State University of Rio de Janeiro in 1988, his MS from the Catholic University of Rio de Janeiro in 1991, and his PhD from Rensselaer Polytechnic Institute in 1994, all in electrical engineering with a focus on power systems. Since 1995, he has been with the Federal University of Rio de Janeiro, where he is now a professor and head of the Power System Group and Laboratory. He has held several leadership roles, including vice chair of the IBR Power System Dynamic Performance Committee, and he was the president of the IBR Rio de Janeiro section, and he's previously served as an associate editor of the IBR Transactions of Power Systems. His research spans power system dynamics, protection and control, robust control design, distributed energy resources, and hybrid AC-DC networks. And with that, Professor Glauco Taranto, the floor is yours.
Okay, thank you, Koji, for the introduction. Good morning, people from the West Coast. Good afternoon, and the other part of the US, and also here in Brazil. We have some colleagues from Brazil also attending. Thank you very much for inviting me here for you today. I will try to be okay. Do you see my screen now?
Yes.
You see,
Perfect.
right? Let me close this here. Okay. Oh, okay, do it like this. Yes. Okay, so thanks for the introduction again. I will try to leave some room at the end for the Q&A session. The title of my presentation, Challenge Posed by the Oversupply of Inverter-Based Resources and Hybrid AC-DC Transmission in the Brazilian Interconnected Power System. Thanks for the Foothill section and Orange County, Richland, and Charlotte sections and chapters for putting together this webinar. I have divided this presentation in three parts. The first part, I will talk about this Brazilian interconnected power system in a brief. I will refer to it as the BIPS. The new solar PVs and wind generation that is coming into the system, and the new long distance embedded HVDC links that are also being already constructed and being constructed in the Brazilian system. Part two, I will talk about the challenges posed by these hybrid AC-DC networks. And I'll show you an application of a proposed angle difference controller for HVDC links. And the last part, I will give you some highlights of the blackout that occurred in Brazil in August 15, 2023, and the actions that were done after the blackout in concluding my webinar. Okay, moving on. Why it's not going? Oh, wait a minute. Okay, so part one, the BIPs. As I said, very high capacity and very long embedded HVDC links came into service in the Brazilian interconnected power system in the last years. Okay. These also hundreds of megawatt scale centralized wind and solar farms are coming into service in the BIPs at a very fast pace. Uncontrollable and unobservable gigawatts of micro and mini distributed generation. Micro here are those generation less than 75 kilowatts, and mini, I mean less than 5 megawatts and higher than 74 kilowatts. Those I'm talking about the behind the meter generation. Photovoltaic, 99.9%, are also coming into service in an unpredicted fast pace. Too many gigawatts so are passing through converters in Brazil, in generation and in transmission, giving rise to unexpected phenomena. Loop flow is one of the main parts of my talk today, is one of such problem. And I will talk about more a little bit in the second part of this webinar. And then we will propose an angle difference controller that will adapt the HVDC links power flow set points to eliminate loop flows while reducing the AC transmission losses. Okay, the BIPs is subdivided in 4 geoelectric regions: the north, the northeast. You can see here in this. Let me put the mouse here. The north here in this picture, and on the right, the northeast, the southeast, and the south. You can. This is a book that was edited by myself and one colleague. You can download this book, and if you want to read a little bit more about the BIPs, you can download this book. Concentration of large solar and wind farms or parks are here in the northeastern area. Okay, most of those very large farms are here in the northeast. Okay. This is the installed capacity right now, present capacity, and the estimated capacity for December 2029. As you can see here, Brazil is still a hydropower house. We have 43% of hydro. If you see 5 more years from now, you see that we are not increasing in the hydro. There is no expectation to increase the hydros anymore in Brazil because they are very expensive now. Natural gas, only 7.4%. Oil, only 1%. Coal, 1.2%. Nuclear, less than 1%. Biomass, 6.2%. And you can see here this MMGD, I call MMGD, which is this behind the meter distributed generation, is becoming the second largest. If you count this as one equivalent generator, the behind the meters is the second large generation in Brazil now. Wind is also 13.8% and solar is 7.5%. So if you add those three here, you are talking about now a capacity of 40% of IBRs already in Brazil. So this is the total generation capacity now is 25,000 gigawatts roughly. Okay. As I said, this is a solar map on the left and the wind map in the right. So you can see that wind and solar, Brazil, the sun shines everywhere, but it's very well concentrated, a lot of radiation in the northeast, and also the wind blows very well in the northeast. That's why in the northeast region, you have a very big farms, solar and wind farms located. Now about the transmission system. Um, those lines that you see here are HVDC transmission lines. The ones in red, they are already in service. The one in yellow here is under construction. Those here that I call not embedded, those 4 lines here and these 3 lines here, they are embedded. When what I mean by embedded HVDC, when the rectifier and the inverter buses are in the same synchronous area. Just when there is a parallel AC path. In these 2 cases here, Madeira and Itaipu, there is no AC in parallel because they connected radially very large hydropower plants into the system. So you can consider that those transmission links, the HVDC links, is part of the generation. And due to the high ratings, you see here, we're talking about 4 gigawatts in this bipole, another 4 here, 4 here. Actually, this is 5, is wrong here. So due to these high ratings, all HVDC links in the Brazilian system employ the LCC technology. Okay, I'm making a comparison between Brazil and China because China is the country that has more HVDC links already in service. But differently from China, Brazil has this AC transmission, which is a strong parallel AC in parallel with the DC links. China, in the other way, does not have very strong AC in parallel with those HVDC transmission systems. And why? And if you look here at this picture and on the right, the density of people, 94% of Chinese live in this on the right of this line here, as you see, and only 6%. So the HVDC brings not the hydros, the wind and solars that they have on the west and send to the east. So there is no way that the power can reverse from east to west in China. So all the HVDC are always in the same direction. I am comparing Brazil with China because we are about the same size. China is a little bit larger. This is a comparable. It's a website that you can compare the size of the countries, and you can see here Brazil and China. So we are big countries, same size of USA, roughly. Okay, this is large amounts of curtailment is happening in Brazil now. This is the actual data that you can take from this website here from the Brazilian system operator called ONS. This is the data for the wind generation and solar generation on September 26th this year. You can see here that the solar is increasing in this day here, 32.5 gigawatts increase. And you see here that when the sun goes up, the wind is going down. Not because of the nature is doing this, but we are curtailing the wind generation because of this huge amount of solar. But here you have an increase of 32, only 16% decrease. Where is the other 16? The other 16 is in the hydros. The hydros is decreasing and the wind are decreasing, are curtailing because the solar is coming. Also, the solar farmers, the solar farmers are also being curtailed in Brazil But the generation behind the meter, there is no way that you can curtail them. They are unobservable and uncontrollable. So when they come, the other generation and the wind and the hydro is going down. Brazil, as the thermal generation in Brazil is small, and then you don't have room to decrease in the thermal because they are only 10% of the generation. This is the same day. You can see here the peak load at noon was 77 gigawatts. This is our nuclear. We have just one nuclear that stays on the base. No change in the nuclear. You can see here generation mix at noon was the load was 77.5. The nuclear was 2 gigawatts, thermal 10, hydro 25.5, hydro wind 7.5, and solar this. If you compare this synchronous machines versus IBR, in this case, the IBRs was more than half of the generation in the country at noon at that day, and all IBRs in Brazil they work as a grid following inverter. Let's just say that if you see here, remember that 32 gigawatts came into place, and where did I had to diminish? I diminished 16% in the hydros and 16% in the wind. If this is just some imagination. If we kept the hydro, not kept the hydro, if you kept the wind and took the 32 out of the hydros, in this case, we would have a problem. The 72% would be in IBRs, and synchronous machines would have only 28%. The Brazilian operator would not do this because of the reliability of the system would not be safe. The system would not be safe with such of this share of 72% of IBRs in grid following mode. Okay, this is how the wind and solar are being put together in Brazil. Those are the states. Brazil is divided in states, like the United States. We have 27 of those. If we take here the ones that I put in red here, which is the south and the southeast, we have 70% of the solar in Brazil in this area. So when the sun goes up here, the wind has to go down, and the wind you see here now the wind. This is the wind share on the states, and 84% of the wind is concentrated in only those 4 states. So when the sun goes up during the day, the wind has to go down in the northeast. So 84% of the wind farms are located in this northeastern region in only 4 states. These 4 states here. They account for 84%. So the daily curtailment of wind farms creates an uneven generation displacement within the BIPs. So it's not evenly distributed, which gives a problem when you have HVDC lines, because this situation can create what we call loop flow. And now I will talk a little bit about what loop flow is, because it's a situation when you can have the DC links putting, let's say, from northeast to southeast in the DC, and the AC pushing power up. So you create a loop flow in the system. And we are talking, remember that we are talking about HVDC links that spans for 2,000 kilometers, 2,500 kilometers. It's a biggie loop flow. So let me talk about now how we can solve the problem of the loop flows created by this unevenly curtailment in the system and HVDCs that are embedded in the AC system. So as we know, if you look at the past, the system where transmissions were all AC. Generations was basically 100% synchronous machine, so no problem to operate the system. But now that the networks are becoming hybrid, so you can have some HVDC links, and this can create what I call the loop flows. Okay, but then added to that, we are replacing, not replacing in Brazil, but we are adding inverter-based generation, that solar and wind. And then we can have a day, we start a day with very low, let's say, wind and solar, very high in the traditional generation. Then you can set point your HVDC links, and okay, you don't have any problems of loop flows. But then what can happen suddenly at the intraday, the solar and wind can go up because it depends of the weather, and then you have to decrease the conventional generation. And if you let your set points fixed, you can create a loop flow just because of this shift in generation. And this is a first time that happened, that was noticed in Brazil, a loop flow, which it was in 7 years ago. This was the first time. This is being was published in this Brazilian conference in November 2019. And you can see here at the beginning of the day, this is the wind generation in the northeast here. The wind was around 7 gigawatts, around 8:30. This line here is the AC transmission from northeast to southeast. And this blue line here is the HVDC there was at that time only one HVDC link in Brazil 7 years ago. Now we have three, and two already in service, and the third one is being constructed. And you see that the wind stopped blowing in the northeast. There was a shift, decrease of 3 gigawatts in some hours. So the conventional generation in the southeast pick up, and then the AC in 11 a.m. the AC reversed from, as you can see here in these arrows going up. And then in this arrow here in the black is HVDC line, green, red are AC lines, and then the DC was pushing power down and AC was pushing down. But they had 1.5 hours to figure out that something was wrong, and then they shut down the DC line in order to get rid of this loop flow that was traveling 4,000 kilometers, or something like the 2,500 miles, just creating losses in the system. Okay, so you have this loop flow. It's very easy to understand the loop flow. You just have a tutorial system here. When you have AC in parallel with the DC, let's say that you have some 20,000 2 gigawatts here generation, 1 gigawatts of load here, 2 gigawatts of load here, and you set up 1,000 megawatts in the DC line. So what happened? Basically you don't have transmission in this AC line here, because you have 1,000 megawatts here, 1,000 going here, and then 2,000 being generated here, 1,000 goes to the load, and 1,000 comes here. But then if you don't control the generation, and generation goes down in this area and goes up in this area, you can create a loop flow, because if you don't change this set point, you create a AC flowing from right to left. And then you see in this picture here, so at this moment here, until this moment here, you have a loop flow, and then you have to change the set point of the DC load if you want to get rid of the loop flows. Okay. Okay, this is also, then we found out that, this is interesting. you can use the set point also for a secondary objective, because what I did here was the following. I started with 0 megawatts in the DC, and then I start playing around and put up to 2 gigawatts in the set point here. And then you see here the set point order in the here in this picture, and then the system AC losses, AC and DC losses. And then you can see here that you can minimize the losses of the system by set point, changing your set points on the DC, because then here you have a minimum. If you have 1 gigawatts here, because then you barely have no transmission in the AC, so you can minimize AC losses playing around with set points and the DC links on those embedded HVDC links. So then we proposed a controller that we call angle difference controller, that you have to measure the angle and the AC bus on the rectifier bus, and the angle of the inverter bus, and then they have to be synchronized, like using a PMU, for instance. And then you can create a controller that will set point, we change the set point of your HVDC line. So the characteristic of our proposed angle difference controller, that should be slow, because you don't want to change gigawatts in the system very fast. So it has to be slow. To minimize or to mitigate the losses, the AC losses, you can have an integral law in this controller, which you try to make the difference equal to 0 of these angle differences. And you have a lead lag block for better transient performance. So that was the idea, and I will show you just a very brief example that is a situation that we have created in simulation, a loop flow in the system. We increased manually, artificially increased the wind and solar in the Northeast. And then we created a situation when the Northeast was pushing AC power like almost 6 gigawatts from Northeast to Southeast in the AC, and the DC was pushing 800 megawatts from Southeast to South. So you can see here that you create a loop flow here. And then we turn on our proposed ADC, and you see here, this is the HVDC power, and this is time, simulation time. You see here, then the 800 going from southeast to northeast is negative in this picture here, and then it starts going decreasing, and then since it's a LCC HVDC, you cannot go directly. You have to wait a little bit, and then you go up. Then this guy goes down. Then you at the end you have a situation that this is a little bit above 2,000 megawatts. You see here is 2100 gigawatts is the final solution here. And then you have both AC and DC sending correctly from northeast to southeast. And this is the voltage and the AC rectifier and the AC inverter buses. They are not very well controlled, because the LCC, you don't have a lot of chances to control the voltage. But then and also you have to dead band that you cannot transmit power less than 10% on the ratings of the HVDC. But then we change. If we were a VSC technology in our HVDCs, then the performance would be better. You see here, then the voltage can be better controlled if you had this technology, and also you don't need dead bands for the flow reversal. But this is just a simulation, because, as I said, we don't have VSCs in Brazil. It is expected in the future that the new HVDCs that we will construct, then they can be of this technology. Just a loss comparison. This is the AC losses for the whole country and the DC losses when we don't have the proposed controller. So the total losses is about 3,000 gigawatts. With the ADC using the LCC technology, we can reduce 6% of the losses. And if we had a VSC technology, ADC, we would have a little better performance and 6.2%. So we can decrease. This amounts a lot of megawatts, okay? Because we're talking about the percentage of the whole country of losses. Just putting a controller. You don't need to have a lot of investments to install the ADC. Okay, some key takeaways of this part. The variability of wind and solar generation combined with the presence of embedded HVDCs in the BIPs call for an adaptation of the HVDC power set points in real time. We believe that this adaptation can be done automatically by controlling the angular difference between the rectifier and inverter voltage phasors. The presented ADC reduces system losses and eliminates the loop flows. And the implementation of the ADC is quite feasible with the use of synchronized measurements from a PMU, for instance. Okay, if you want to further reading, we have some papers on this. Just print this page, or you send me an email. I can give you more reference to this ADC. So for my last part, I will talk a little bit about what happened in the Brazilian last blackout. Was August 15, 2023. It started at the triggering was at 8:30 a.m. Let me do a disclaimer because I don't work for this Brazilian operator, but all the information was obtained from this official ONS report. Sorry, it's in Portuguese. There is no English version here for this. Is more than 500 pages of this report, and then I will give you some highlights of what I found from this report. Apologies here because some texts in the graphics that I will show you will appear in Portuguese, but I think I can. I think you can understand that. And also, I did this presentation last year in the task force that I chair in the Power Systems Dynamic Performance Committee. It was in Seattle last year. So some of the slides I took from that presentation, and I updated after that. I will skip that because I already talked about this. Okay, this is the situation, the T0 minus, let's say, just before the what happened. So the situation was like that. This is the Northeast was exporting generation to the rest of the country, and you can see here this is the limit of this transfer from Northeast to this North, and here's the limit of Northeast to Southeast. And you see that the system was pretty close to the limits or export limits. And here you see the generation in the Northeast region. So you had 2.5 gigawatts hydro, thermal almost nothing, 16 giga of wind, and solar 3 gigawatts. So 87% of the generation in the Northeast was coming from IBRs. So if Northeast was a country, you would have a very high share of IBRs. And the load in the Northeast was only 10 gigawatts, which means that the IBR generation was twice the load in the Northeast region. So they were exporting the 100% of the same size of the load that they have inside the system. They were exporting also the same amount. Okay, and I have to say that Brazil is in South America, and we have neighbors, but our electric connection to our neighbors is very weak. We cannot rely in any other neighbor to help us out, and also the other way around, because the South America is not very well connected among the countries. The triggering event started in this part here, was in the northeast, was an unfaulted transmission line, 500 kV transmission line that tripped. And the green dots means that load was shedding in all those points, which means that load was shedding all over the country. A total of 22.5 gigawatts was shed. This was 31% of the load at that time. So 1/3, basically, the country was down. In the north, 100% was shut down. In the northeast, 61% was cut. In the southeast, 20%. In the south, 20%. This is the point. This is a localized one-line diagram of the 500 kV lines. All in red are 500 kV lines. There is one transmission system here, 230 kV, but it's not that important. And this line here was the disturbance began in this line at 8:30 a.m. This line tripped without any short circuit. The trip was caused by the logical incorrect action of the SOTF, switch on fault function. This is area is the northeast. This is the north. I'm showing here the voltage at the T0 plus 530 milliseconds. You can see here. This is T0. This is the oscillography of the system. And you see here that this is the load, the current in this line. And you see that the current goes to zero. The current was 2300 amps at that time. This two voltage, the 0.92 per unit in Pidutra and 0.68 in Gonçalves, was only half a second before this line tripped. So you see that there was a huge sag in the voltage in the system. So a huge amount of reactive power came from north to northeast, trying to raise the voltage that was down in the northeast. Okay, 0.68 per unit, half a second after this line tripped. These are PMU measurements here that you can see. So you can see here, this is the half second span. You see that the voltages were fine. And after half a second, the voltage in many places here, those are the star here in the right are those places that we had PMUs. This is the line that tripped. And then you see here a huge voltage sag. And then after that, so the Q was flowing from northeast from north to southeast. And here is the voltage. This is quite of intriguing because you see that the voltage bounced back after the next half second. Okay, this is the second problem. The first problem I already talked was that line, the unfaulted line that tripped. The second problem was this line here. So this line is this line. Let me see if is this line over here. This line, Pedutra Esperanza. This before the problem, this line was with 1300 amps. In half a second jump up to 2100 because of the Q. This is basically reactive current. And then turn off because the second problem was out of step protection. You see here the impedance plot in one of those in this line here, and the power the out-of-step protection tripped these 3 lines here that is you see with the stars. There's 3 lines, but I'm showing the current of only this line. So the 68 out-of-step tripping tripped these 3 lines, half a second of the problem. Then the system was deteriorated already, and with this line, then a lot of problems, a cascading of failures. I will not show you all the whole thing, but then the thing tripped. And this is the voltage of this north side, let's say the good side, but even the good side, you see that the voltage dropped to 0.92% and then was turned off. Okay. Then this is also a larger window of those voltages. You can see here the out of step, the swings of voltage, and here the frequency of the system. The frequency was not a big problem. You see here, after half a second, so it was not a frequency problem. Was a reactive problem, reactive power problem. Then the situation was like that. After that, the operator got the operating point and simulated with the same triggering event. And you see here voltages on simulated voltage, and you don't see any problem. You don't see any problem. And then if you compare the simulated and this is a voltage in this ASU 3 500 kV bus. Red is PMU measurement, and blue is simulated. Then you see that the operator saw no problem with the models that they had. That's why the system was they should be safe, secure with respect to the models, but the reality was the red curve. Then also reality against simulation. Red is the measured active power in one of the wind farms. This is one wind farm, reactive power injection, and the simulated was the blue one. So you see that in the models, the reactive power was responding correctly, but actually the reactive power did not increase. Key finding: the disturbance analysis revealed that the in-field control performance of wind and photovoltaic power plants, particularly with respect to dynamic reactive power support, was significantly inferior to that predicted by the computer models submitted by the stakeholders and represented in the BIP's official electromechanical transient database. So what they did after that, they took dynamic database, was manually adjusted to approximately capture the PMU measurements. So they degraded. They did a degradation in the IBR control performance in the models to try to get the same response. So you see here a third picture, which is the green line. The green line is the adjusted database, and you see here the OST instant when in the simulation when tripped, and the out of step instant when the system tripped. It was at this point here. So you see a better approximation with the degraded models. As a consequence, to maintain the BIP's reliability, okay, sorry, they degraded when they stopped also, so they had a reduced security region now with the new adjusted models. As a consequence, to maintain the BIP's reliability, curtailment of the inverter-based generation increased following the August 16, 2013 blackouts. Actions that were taken after that. A data set sanitization. So they are trying to make it that the model can respond to the in-field performance. So model validation was enforced. Then you ask me, but they didn't enforce before? Yes, there was in the let's say in the grid code that the model should be validated, but there was no consequence if the ones that don't do that. But now they are enforcing more. Optimization of the control parameter settings for field deployment controllers. Also, many of the controllers were very slow in the controlling the point of common coupling, and then they are optimizing some control parameters in field. Commissioning speed up of already licensed transmission assets. A recommendation and the specification of new synchronous compensators or new synchronous condensers. So 6 synchronous condensers with a capacity of minus 200 plus 300 megavars, and one synchronous condenser of minus 90 and plus 150 megavars were bid last month. And also the deactivation all out-of-step functions deployed in the northeast and southeast interconnection. So they turn off the out-of-step protection, and then they will rely that the electrical centers will be formed, and then the distance protection, the distance function of the distance protection will open the lines, but not as a the 68 OST function. Okay, in conclusion, to give you some room for Q&A, like many power systems around the world, the BIPS is also facing the growing challenges associated with operating a grid with high penetration of IBRs. To ensure reliable operation under these new conditions, two elements are essential: accurate IBR models and validated controller performance that reflects true field behavior. In hybrid AC-DC networks where bulk power transfers can reverse direction, DC-like power set points, DC-link power set points must be automatically adaptable. Close attention must be paid to the loop flows. Some lessons learned from the Brazilian blackout. IBRs did not provide sufficient fast dynamic reactive power support at their points of interconnection, and the legacy out-of-step protection schemes proved inadequate for the new operating paradigm driven by large IBR contributions. So this, I close my presentation. I thank you all for listening, and I am now open for the Q&A. Thank you.
Thank you, Glauco. Very impressive presentation, and then good to know the actual event in Brazil. And then if you have any questions, please use chat window and then type your questions because we have more than 10 audiences today. But before that, so the Glauco, do you know, so the trigger of the event in Brazil in 2023 was just a typical N-1 contingency in the transmission grid, right? Like a high voltage network. And then it is unlikely that we have like a 62% voltage level at one of the buses. And then I'm wondering if we have like lots of disconnection of renewable energies at the same time. Like, do you have enough fault write-through requirement for the renewable energy resources in Brazil? If so, they must keep connected. But for example, if the fault write-through requirement are not satisfied in many inverter-based resources, and then that event can be a trigger to disconnect lots of renewable energy resources, and that leads to the equivalent increase in loads because the net load will increase after the disconnection of inverter-based resources. And then if we increase loss of loads, then probably we have a significant voltage drop. This is my kind of impression or intuition. But so just I'm curious about do you have any recorded data about the possible disconnection of inverter-based resources, especially in northeast area?
Yeah, they have a lot of much more information. As I said, the report is 500 pages, but no, they have fault right through grid code
Oh.
for Brazilian. They did not disconnect before those transmission lines stripped. So the second event was the out of step protection that turned
Mm.
those three lines out. The generation was still on. The solar and the wind parts, they were on at that point. They didn't trip so fast. Because you see, I show you that the voltage bounced back, and then they didn't have enough time to disconnect the wind and solar. The problem was reactive support, dynamic
Mm.
reactive support. The models were giving the reactive power, but the reality didn't give. That's why the voltage dropped. And then the out of step protection tripped. So the first event was uh, was a something that could not happen, was an untripped fall, unfaulted trip. Okay, but it's okay. As you said, this is an n minus one. This should not be a problem. And in the models was not a problem. The simulations showed well after they did that triggering, everything was fine. But the problem was dynamic reactive support. And then this led to out of step protections. Tripped in the line, and then the system was already degraded. And after then, the n minus one situation became n minus four in half seconds, and then there were more than 60 transmission lines stripped after that in cascading events. So that's why the north was completely shut down, in the northeast almost completely shut down. The north, the south, and the southeast, they cut they had a scheme that they shed loads, and then they opened, they became isolated from the north and now southeast, and then they could keep 80% of their load in the
I
south
see.
and southeast.
I see. Thank you for this clarification. And we have one comment in chat window. So, Glago, can you open the,
The chat.
yeah,
Okay.
yes, the chat window?
Okay, I want to know if there were StatComs connected in the Brazilian system with the PV and the wind farmers to support the reactive power during the blackouts. No, there is no StatComs in the farms. There is no hybrid farmers in Brazil yet. That could help. Um, and also synchronous condensers could also help. That's why now there was this standard last month, so they are putting those synchronous condensers. Uh, I think they were technology agnostic on those. In that no, I think that was synchronous condensers oriented. I think don't know StatCons could go in that tender, but I agree that StatCon also could help. Yeah, but there was unfortunately, no synchronous condensers and no StatCons.
Yeah, thank you. And also, have you ever considered like a minimum percentage of synchronous generators in Brazil? Because at that time you told us that the percentage of synchronous generator was around 30% or so, so very low percentage, and there are too many renewable energies right before the event happened. So,
Yeah,
in other countries, I think we try to keep at least like a 40 or 50% of the synchronous generators all the time.
yeah. The Northeast was very percentage-wise was 87%, but the whole country
Mm.
was that point was 40% only
Oh,
in the whole country.
I see.
The if Northeast was a country, then I don't think the ONS would operate in the system like that. Uh, but uh, but no. Now, but I show you some numbers of 2 months ago, and at midday at noon, the system was 52% with IBRs in Brazil. and 48. So I think they are operating around 50-50. That just I'm guessing now, but I should not be too wrong here. And so the curtailment is because of that, because they are curtailing the wind in order to keep this percentage of IBRs, I think, around 50%.
I see. What about
Yes.
the grid code requirement in Brazil? So, for example, you talked about the missing dynamic reactive power support from inverter-based resources. And then, for example, if we consider the latest IEEE 2800, like in the United States, they started to require the dynamic reactive support for large-scale inverter-based resources. And then, do you have this kind of direction in Brazil after that event happened?
Yeah, no, there is code. They have to work like they were a synchronous generator. So this is in the grid codes, and that's why the models were giving the reactive support. Problem was that the field controls were not performing like the models. So they were now trying to fix that. They have doing after the blackout. They are trying to fix that, but they are still not going into the grid forming IBRs.
Mm,
They are still keeping the all of them 100% are still grid following. But there was some situations that the decentralized plant controller was too slow. Some of the farms were using a kind of SCADA
mm,
time constants for controlling the point of interconnection, and then this is not allowed anymore. So the local, let's say the unity controller was fast, but the central controller was slow, and then this is one of the problems. And then has this is being fixed now.
I see. And also, because we have already introduced lots of renewable energy resources, and we cannot directly change the control functions, right? If we introduce a new one, of course, we can ask the new inverter-based resources to integrate the dynamic reactive power support function. But yeah, so it is kind of challenging,
Yeah,
I
no,
feel.
the technology, this is not a problem for the OEM. They have all this, they can do that. But the problem was that some of the farms are not doing that. They should be, the performance was not doing well uh, because they were not turned on. Let's say some of them probably
Oh,
didn't turn on because it's not a problem of the technology. It's a problem that the field was not reflecting the models. That was the main problem.
got it.
Yeah.
Yeah, thank you. So, any other questions from audiences? Um,
Question from online.
yeah, sure. Yeah, please go
Excellent.
ahead.
A great presentation. A question on how long did the blackout stay powered down? In other words, how long was the time to fully recover the network in Brazil?
Yeah. Yeah. Okay. I will try to remind, but in the south and the southeast was not a big problem because they shed load in a certain amount and they could stay with the system on. So those kinds of loads that you shut down that as you want, as you wish, it's easy to come back. But the problem was in the north and the northeast because they really shut down. Then you have to recover, to recompose the system from almost the ground zero. And then some of north and northeast, they took around 4 to 6 hours to come back. Yeah. It's
What
not
causes
Brazil. Brazil is not usually Brazil is not the recompose the recomposition or recover. I know the word exactly the word. Uh, usually is not too long, because as I showed in the numbers, the BIPs number, we don't have a lot of thermals. So hydros you can put on very fastly. But even though in the Northeast, and in the Northeast was also a problem, because remember that before the problem, they were with 87% of IBRs, and those IBRs agree the following. So somebody has to form the grid before they come to the system again. And then it took some hours, I would say. It's around, I would guess, 4 to 6 hours to recover the whole system.
So
There was also, it seemed at the very beginning that they were running over the nameplate capacity on the power transfer. How did that
Yeah,
happen?
yeah, no, I would say that they were at the limit. Was just in one of the limits was a little 1 or 2% higher, and then I would say that they were not violating the limits, but they were at the limit. This
Yes.
is an
Okay.
important point. Yeah.
Thank you.
So Syed, do you have a question?
Yes, just one more question. Thank you very much, Dr. Toronto, for a very great presentation. During the blackout in 2023, I see that in the Northeast, 63% of the system was uh, actually down, or was it working? I just wanted to know that.
No,
Furthermore,
I see. No, go ahead.
and then the second part of the question is, usually we do see that these PV farms and wind farms, they feed to the fault, right? They feed high current to the faulted area.
Yes.
It will be interesting to note like how much of the contribution of these PV and wind farms were there to this fault, like how much per unit where we were feeding to this fault, and could have been protected, could have been like we could have, or Brazilian system could have, put the PV farms and wind farms out of the system. It would be interesting to see like what sort of protections were there in place for these wind farms and PV farms. So if you can comment on that.
Yeah. Uh, no, I think the number I showed, 60% of the Northeast, was the load that
Okay,
shed
gotcha.
after the blackout.
Okay,
Yes.
okay,
So
okay.
it's and the in-feed current, reactive current, they were in feeding. Let's say in the models, the currents
Mm-hmm.
were in feeding, but not in the field. And I
Ah,
cannot tell you the percentage of wind and solar that were correctly and the ones that were not correctly. I don't have those numbers,
this
but
is this is really
yes,
interesting because
yeah,
if the models were wrong, uh, then there was something that was missing in the model somehow, because I don't know how a PV and wind farm cannot feed a fault, right? That's an issue because you were showing in the simulations as well that you were not seeing the right reactive power current feeding from the PV and from the wind farms. So was it a mistake on behalf of the vendors, or was it a mistake on behalf of the Brazilian operator who,
yeah, yeah. I don't want to blame anyone here, but
okay.
the problem was that the ONS was relying on models that put the system in secure, and that the point that the system was operating was insecure, but
uh,
they didn't know that, okay, because the models were, let's say, giving the reactive power support, and the
mm,
field were not giving the support. That's why I show you one reactive comparison. When
yeah.
the models inject reactive current
Hmm.
in the system during the fault, in fault is a control that is a fault in injection, right?
Right.
But
Yeah.
some of the farmers were not feeding in the reactive current. That's why the voltage dropped.
Correct. Of course.
The voltage dropped, and then there was a huge amount of reactive power being imported from the north.
From the north side, yeah.
And this very high current in those transmission lines triggered the out of step protections between the north and northeast. And then you have you cascaded the problem.
Yes, correct. All right. Thank you very much. Thanks.
Okay, sure.
So Glauco, if you have time, can you check the chat window again?
Okay.
We have one quick question.
Do you think grid forming IBRs, virtually synchronous generators, instead of grid following IBRs, can help strengthen the grid to prevent future such events? Okay, that's a good question. I would say that if we had some grid forming IBRs, would let's say would help more, but I don't think it would save the system. This is my view. At this such a big problem that the system was facing, because of the grid. Oh, because if I think if the grid following were with the correct control in the field, that would help too. I don't think this is a problem of only if we're grid forming would save the system. No, if the system would be grid following as the models were, I think the system would be saved, even being grid following. But I agree with you that the grid forming is even better for the security of the system in this in those contingencies. But I don't think that they would be a solution for that problem.
Quick question.
Yeah, please go ahead.
Is it possible to test, is it practical to test in practice the reserves provided by a distributed energy vendor, or do we just have to take their word for it?
Could you repeat?
Sure. Is it practical in practice? In other words, can it actually be done on a live grid to test periodically that the vendor can provide the reserves which he is required to provide? Is that possible to be done?
Okay, it is possible, but it's not easy, I would say, because testing is always not the.
I think, yeah, he's offline.
Oh, do you
Yeah,
hear
you're
me?
back. No,
Okay. Oh, I was down?
Yes.
yes,
Okay.
a little bit.
Repeat the last sentences.
Okay. I was saying that it's possible, but it's not easy to do the testing again. But the ONS is forcing them to do that. They are forcing the OEM to give models more, let's say, more. More correctly, or more, not correctly is the word, but more detailed for the Brazilian tools, because the ONS uses Brazilian tools for transient stability. I mean RMS, positive sequence dynamic stability software, and also load flow. But there is some, I know that there is some, the OEMs, they don't want to open completely the models. So they can give you black boxes. And this is a big problem, because of the system, the official transient stability system that the Brazilian operator uses, you cannot give a black box to that software. It has to be open. And then this is a situation that's not still unsolved. And then this is
Well,
an ongoing problem.
But
Do you hear
Professor
me?
Toronto, yes, if they can give you an equivalent circuit for the black box, but if it's not turned on and you don't know that until the blackout occurs,
that's true.
That's a
That's
huge
true.
problem.
Yeah, that's true. What happened was that they were on in the models, and some of them were off in field. So you cannot operate such a problem like that you can rely the models. Actually, the ONS is not completely confident in the models as I speak now. That's why the curtailment increased. The curtailment of wind and solar farms increased after that blackout because
I look forward
they
to how
don't.
they resolve it.
Excuse me?
I look forward to how they resolve this situation. It seems somewhat political, but there's got to be a solution. Otherwise, you spend
That,
a lot of money to have very high safety reserves.
that's true. That's true. I agree with you. Yes. Thank you.
Thank you.
Thank you.
Okay.
Yeah.
Is there any more? No. Okay, go ahead.
Yeah, I think the time is up, so we should finish this webinar now. So anyway, we deeply appreciate this exceptional presentation, and then also very few experts in the world can explain the actual event of the scale so clearly. So thank you, Glauco, and also the Dr. Taranto. And then everyone, the next webinar will be held next week on December the 1st. And we will invite a young EPRI engineer, Dr. Das, who will talk about the parameterization of IBR models. So that is kind of related to our discussion. So if you have time, please join the next webinar. Thank you for your time today. And again,
thank you. Thank you, Koji. Bye.
Thank you,
Bye,
Glauco.
everybody.
Yeah,
Thank you.
bye for now. Thank you.
Bye-bye.